Section 5.2, Right Triangle Trigonometry. There are 6 trig functions that we'll need to know: the sine, the cosine, the tangent, the cosecant, the secant, and the cotangent. Each of them are abbreviated with 3-letter abbreviations. In fact, 5 of the 6 are the first 3 letters of the word. You'll need to be especially careful with cosecant because that one has a different abbreviation, CSC. We need to define our 6 trig functions. Each definition will be a fraction. For the sine of theta, the definition is the length of the side opposite our angle theta divided by the length of the hypotenuse. The hypotenuse is always the side that is across from the right angle. The definition of cosine is the length of the side adjacent to angle theta divided by the length of the hypotenuse. Tangent is the opposite over the adjacent. Here's a memory device. There's several that you could use. This one is some old horse caught another horse taking oats away. Some old horse reminds us that the sine is the opposite over the hypotenuse. Caught another horse reminds us that the cosine is the adjacent over the hypotenuse. And taking oats away reminds us that the tangent is the opposite over the adjacent. The definitions for cosecant, secant, and cotangent. For cosecant, we have hypotenuse over opposite. The secant is hypotenuse over adjacent, and the cotangent is the adjacent over the opposite. Here's a summary of our 6 trig functions using 3-letter abbreviations. Remember, with our triangle, the hypotenuse is always across from the right angle. The opposite and adjacent are the 2 legs, but it depends on where theta is. If theta is down here, then the opposite would be the side across from it, and this side down here would be the adjacent. If theta is instead the angle up top, if that's the angle we end up to be interested in studying, then the opposite would be down below, and the adjacent would be over here because it's the side next to theta. Example 1, we want to find the 6 trig values of theta in this figure. The first thing we notice is that we have the opposite of theta is 3. The leg that's adjacent to theta is 4, but we don't know the hypotenuse. We can use the Pythagorean theorem to find c. C squared equals a squared plus b squared. So we substitute in a and b, and then we simplify. So we get 9 plus 16 is 25. That's c squared equals 25. So c equals the square root of 25, which is 5. So we can replace our c with 5. Now we want to find the 6 trig values. Starting with sine, it's the opposite over the hypotenuse. The side opposite theta is 3, and the hypotenuse is 5, so the sine of theta is 3/5. The cosine is the adjacent over the hypotenuse, so that's the 4 over the 5, that's 4/5. Tangent is opposite over adjacent, so from theta's perspective, the opposite is 3, the adjacent is 4, so we get 3/4. Moving on to the cosecant, that's the hypotenuse over the opposite, and so that's 5 over 3. The secant is the hypotenuse over the adjacent, 5 over 4. And finally, we look at the cotangent, which is the adjacent, which is 4 over the opposite of 3. We want to look at function values for some special angles. One of the special angles that we deal with is 45, and a right triangle that has a 45-degree angle, or in radians, that's pi over 4. That's an isosceles triangle. It means that the 2 legs are equal length. In the diagram here, we have both legs equaling 1, and then we could use the Pythagorean theorem to see that the hypotenuse is the square root of 2. We can use that to find various trig values of 45 degrees. Since the cosecant is the hypotenuse over the opposite, that gives us the radical 2. The length that's across from 45, the opposite, is 1, and that reduces to radical 2. The secant is the hypotenuse over the adjacent, so that's again radical 2 over 1. Since the opposite and the adjacent are both 1s, we get the same value for both of these. And then finally, the cotangent is the adjacent over the opposite. So from 45 degrees perspective, the adjacent is 1 and the opposite is 1. So that gives us 1 over 1, which reduces to 1. Moving on to some other special angles, we are interested in 30 degrees and 60 degrees, which 30 is pi over 6 and 60 is pi over 3. And inside a 30, 60, 90 right triangle, the measure of the side that is across from 30 is always 1/2 the hypotenuse. If the side across from 30 is 1, then that's half the hypotenuse, which would then be 2. And the Pythagorean theorem would allow us to find the radical 3. In this example, it wants us to find the tangent of 60 and the tangent of 30. The tangent is the opposite over the adjacent, but the tangent of 60, we have to make sure we're looking from the 60's perspective. Its opposite is radical 3. Its adjacent is 1. We end up with radical 3 over 1, which reduces to radical 3. To find the tangent of 30, we have to be sure we're looking at 30's opposite, which is 1, over 30's adjacent, which is radical 3. And so we end up with 1 over radical 3. We're not allowed to leave a radical in the denominator, so we call this process rationalizing the denominator. We multiply by 1, but it's a special one. It's radical 3 over radical 3. And then we simplify. The top gives us radical 3, and the bottom gives us 3. This chart just summarizes many of the important values that we'll be working with. We could obtain these ourselves from the last two special triangles that we were just looking at. In fact, we found a couple of these values, but the sine, the cosine, and the tangent of 30, 45, and 60 degrees in simplest radical form are shown here. Now we're going to look at some fundamental identities. Identities are equations that are always true, and you may have noticed that the sine is the opposite over the hypotenuse, and the cosecant is the hypotenuse over the opposite. So that makes those two reciprocals of each other. So it's always true that the sine is 1 over the cosecant, and the cosecant is 1 over the sine. These two trig functions are reciprocals of each other. The same is true for cosine and secant. They are reciprocals of each other. And tangent and cotangent are reciprocals of each other. Additionally, we have a quotient identity of the tangent equals the sine over the cosine, and the cotangent equals the cosine over the sine. In this example, we're given the sine and the cosine, and we're asked to find the value of the other 4 trig functions. Of the 6 trig functions, we know the sine is 2/3 and the cosine is radical 5 over 3. To get the other 4 values, we're going to use our fundamental identities. Our strategy will look something like this. We are already given the sine and cosine, so those are done. We want to find the cosecant, which we can do because it's the reciprocal of the sine. We need the secant, which we can find because it's the reciprocal of the cosine. To find the tangent, we can use either a reciprocal identity or a quotient identity, but notice at this point in the problem, we wouldn't yet know the cotangent, so we'll have to use the quotient identity, tangent is sine over cosine. And then finally, we need to find the cotangent, and we could use either one of these because by then we'll know the tangent, so we could say it's the reciprocal of the tangent, or we could use the quotient identity because we'll know the cosine over the sine. When you have a choice between a reciprocal identity and a quotient identity, typically the reciprocal identity is easier, so that's the one that we'll use. So looking at our example, of the 6 trig functions, our strategy will look something like this. We have 2 that are given. Tangent is sine over cosine. Cosecant is the reciprocal of the sine. Secant is the reciprocal of the cosine. And cotangent is the reciprocal of the tangent. Let's start with tangent being sine over cosine. Sine is 2/3. The cosine is radical 5 over 3. To reduce this complex fraction, we take the top fraction, and instead of dividing it by the bottom fraction, we'll multiply it by the reciprocal of the bottom fraction. The 3's cancel. That gives us 2 over radical 5. We can't leave a radical in the denominator, so we'll multiply top and bottom by 1, which is radical 5 over radical 5, giving us 2 radical 5 all over 5. To get cosecant, that's the reciprocal of the sine, and so that's 1 over the sine of which is 2/3, which gives us 3 over 2. Now, here's a little tip. Rather than writing the cosecant as 1 over sine as 1 over 2/3 and then dealing with that fraction, you could just flip the sign directly. Since we were told the sine is 2/3, we can just find its reciprocal, 3 over 2. Now we have to find the secant. The secant is the reciprocal of the cosine, so that's 1 over radical 5 over 3. which the reciprocal is 3 over radical 5. Again, you could have just flipped the cosine directly to get to the point we're at, but now we have to rationalize the denominator by multiplying top and bottom by radical 5, and that simplifies to 3 radical 5 all over 5. Finally, we need the cotangent. The cotangent is the reciprocal of the tangent. We can flip that value. We have to rationalize the denominator, and we get radical 5 all over 2. Now, here's a tip that could save you some time. Notice that the cotangent is 1 over the tangent. So what we did, which was logical, we took the 2 radical 5 over 5 and we put it down there, which is the same as just flipping this value and putting the 5 on top and the 2 radical 5 on the bottom. But actually, both of these strategies are inefficient. There's a way to go directly to this answer based on the work we did for tangent. Notice that before we rationalized the denominator, we had 2 over radical 5. When working on the tangent, we didn't like having the radical 5 in the denominator, but if we're going from tangent to cotangent, it's good to have the radical 5 in the denominator because you can flip it directly at that point and get radical 5 over 2. Next, we're going to look at the Pythagorean identities. The Pythagorean identities involve squaring trig functions. Notice that the 2 might seem like it's in an awkward place, but that's opposed to putting it above the theta. If it was above the angle, it would mean to square the angle. This doesn't tell us to square the angle. This means we take the sine of the angle and then square it. And so you'll notice that each of the 6 trig functions is represented in these 3 identities. And we will use these to find various trig functions like we did before when you know some trig functions to help you find others. Before we do that, we want to look at some algebraic manipulations that put these in other forms. The sine squared theta plus the cos squared theta equals 1 is equivalent to the cos squared theta equals 1 minus sine squared theta. Notice what we did is we subtracted sine squared from both sides. And then if we go back to this original one and instead subtract cosine squared from both sides, that leaves just the sine squared on the left, and then on the right we get the 1 minus the cosine squared theta. These 3 are equivalent, so they're really just one identity, but you'll sometimes see them in their alternative forms. Likewise, 1 plus tan squared theta equals secant squared theta. If you subtract 1 from both sides, you get this version. If you go back to this top one and subtract instead the tan squared from both sides, you get 1 equals secant squared minus the tan squared. And then finally, cotangent squared equals cosecant squared minus 1. And if you leave the 1 on the left and subtract the cotangent squared, you get 1 equals cosecant squared minus cotangent squared theta. In this example, we're given the sine of theta is 1/2, and we're looking for the cos of theta using a trig identity. Notice that the identities we had before will not be sufficient in this problem because with the sine, we're able to find the cosecant using this reciprocal identity, but given the sine, we won't be able to find any of the other 4, and the one they're asking for is the cosine. So what we recognize is that the sine and the cosine are related to each other in a Pythagorean identity. Sine squared plus cos squared equals 1. So we substitute in the value we know for sine, and that's a 1/2. We square the 1/2, giving us 1/4. Subtract 1/4 from both sides. That reduces to 3/4. That's cos squared equals 3/4. So we take the square root of both sides. So the cosine equals the square root of 3/4. And when we reduce that, the top simplifies to radical 3, and the bottom, the square root of 4, is 2. Trig functions also have something called complements. 2 positive angles are complementary angles if their sum is 90, or in radians if their sum is pi over 2. Any pair of trig functions, f and g, where f of theta equals g of 90 minus theta, or g of theta equals f of 90 minus theta, are called cofunctions. The value of a trig function of theta is equal to the cofunction of the complement of theta. So cofunctions of complementary angles are equal. That tells us that the sine of theta always equals the cosine of 90 minus theta, and that the cosine of theta always equals the sine of 90 minus theta. Each trig function has its cofunction, so tangent and cotangent are complementaries. In fact, that's what the co stands for in all of these. It's complementary tangent. It's the sine and the complementary sign, but we say co for short. The secant of theta equals the cosecant of 90 degrees minus theta. These identities will be used in degrees, but we also can use them in radians. If just replace 90 with the radian equivalent of pi over 2. Let's look at some examples. Example 6a, the sine of 46. Well, the cofunction is cosine, so we want the cosine of 90 minus 46, and that means we have the cosine of 44. This tells us that the sine of 46 degrees will equal the cosine of 44 degrees. In example B, we have the cotangent of pi over 12. We want to deal with the cofunction, which is the tangent, and since this is in radians, we'll use the version of the formula that's in radians and substitute in our angle. So the tangent of pi over 2 minus pi over 12, we need to get a common denominator of 12. So pi over 2 is rewritten as 6 pi over 12, and then when you subtract, you get the tangent of 5 pi over 12. So the cotangent of pi over 12 will always equal the tangent of 5 pi over 12. Example 7 is an application problem that involves right triangle trig. In the diagram, this irregular shape is a lake, and the distance across the lake is unknown, labeled with an A. A surveyor took the following measurements. From point C, looking directly across the lake, they went at a right angle, a distance of 750 yards, to point A. Then they looked back at point B and measured that angle between the original point C and the point across the lake. They measured that angle to be 24 degrees. The question we have is to use that information to find the distance across the lake. This question will involve tangent. We have to select our trig function carefully, and we'll always choose from sine, cosine, or tangent for these. But the reason we chose tangent, we know 24 degrees, and we know the 750 yards is the leg that is next to 24, so this is the adjacent. So knowing the adjacent and theta, I'm looking for the side that's across from 24. I'm not interested in the hypotenuse in this problem, so the unknown side is the opposite, so that lends itself well to tangent. Let's fill in these values. The 24 degrees, the adjacent side was 750, and the unknown side is side A. Be careful not to confuse the A for the side with the A that is the first letter in the word adjacent. So now we can cross multiply. Think of the tangent of 24 as being over 1, so A times 1 is A, and then the 750 times the tangent of 24. And then we can use our calculator on this. Be careful when you use your tangent button. You have to make sure that you are in degree mode because this is 24 degrees. So you multiply 750 times the tangent of 24. So the distance across the lake is approximately 333.9 yards. Finally, for our application problems, we're going to want to know the definition for the angle of elevation and the angle of depression. In this building, there's an observer up here on the maybe 4th floor that is looking up at an airplane. They also could look straight out along the horizontal. And finally, they're looking down at this car that's down on the ground. The angle of elevation is made with the horizontal up to the sight line that is above the observer. And the definition of angle of depression is with this car, it's the angle that's made with the horizontal down to the sight line to the object that is below the observer. Next, you'll apply that in your homework.